In this lecture, I am going to present what are the different step-by-step procedures for the analysis of fixed beam. Then I would like to solve two problems on the fixed beam with uniform distributed load for some distance. So first coming to the step-by-step procedures for analysis of fixed beam. Let MA and MB be the fixed end moments. The beam may be analyzed in the following steps. So first consider the beam as simply supported condition and draw the free bending moment diagram due to external loading. Then due to the effect of end couples MA and MB alone, draw the fixed bending moment diagram. But here you don't know the fixed end moments MA and MB. Then determine the fixed end moments at A and B, that is MA and MB, using the moment area method. So you can find out the fixed end moments MA and MB by using the moment area method. So in moment area method, there are two theorems. So the first theorem, that is the total area of the free and fixed bending moment is 0. That is A1 plus A2 is equal to 0. A1 is the area of the free bending moment diagram and A2 is the area of the fixed bending moment diagram. So the summation of A1 plus A2 is equal to 0. Then the second theorem, that is the total moment of the area of free and fixed bending moment diagram is 0. So here you have to take the moment of the free bending moment diagram from the support A or support B plus the moment of the area of the fixed bending moment diagram from the support A or support B. So if you are taking from the support A, then you have to take the moment of the free bending moment diagram and fixed bending moment diagram from the support A. So this is equal to A1 x1 bar plus A2 x2 bar is equal to 0. Then after using these two equations, then you can find out the fixed end moments MA and MB. Then after knowing the MA and MA, then you can draw the final bending moment diagram by combining the free bending moment diagram and fixed bending moment diagram. Then by taking both external loads and fixed moments at the ends, determine the reactions for the fixed beam. Then determine the shear force value and draw the shear force diagram. Then find the point of contraflexure distance. Also you can find out the maximum bending moment where shear force is 0. So here you have to assume the free bending moment diagram is positive and fixed bending moment diagram is negative. So the area of the free bending moment diagram is equal to the area of the fixed bending moment diagram. A1 is equal to A2. Similarly, the moment of area of free bending moment diagram from A is equal to the moment of area of the fixed bending moment diagram from the same end A. That is A1 x1 bar is equal to A2 x2 bar. So using these two equations, so you can find out the fixed end moments. Then after knowing the fixed end moment, then you can draw the combined bending moment diagram. Then you can draw the shear force diagram. Then you have to find out the point of contraflexure. Then you have to find out the maximum bending moment. So these are the steps you have to remember, so that you can find out the moments at the end of the beam. Then you can draw the bending moment diagram and shear force diagram by moment area method. Then coming to the first question. So this is the question. A fixed beam of 4 meter span carries a UDL of intensity 15 kN by meter up to mid span, draws SFD and BFD. So here this is the fixed beam and here the span is given 4 meter and the load is given 15 kilonewton by meter up to the distance 2 meter. W is equal to 15 kilonewton by meter and L is equal to 4 meter. So first you have to take the simply supported condition, then you have to draw the free bending moment diagram, then you have to find out the bending moment at both ends, then you have to draw the fixed bending moment diagram, then you can draw the combined bending moment diagram. Figure 1 shows a fixed beam AB of span 4 meter carrying a uniformly distributed load 15 kilonewton by meter for a distance 2 meter from the end A. So consider any section X at a distance X from the end A. Consider any section at a distance X from the end A, and you have to take a small elemental length dx. The load acting on the elemental length is equal to W into dx, and here the UDL is given 15 kilonewton by meter. So on this elemental length, the concentrated load is acting 15 into dx. First you have to take the simply supported condition, only you have to take the external load, and due to this external load you have to find out what is the reaction at both ends, then you can draw the free bending moment diagram. This is the free bending moment diagram and this is the simply supported condition. So here the reaction at both ends, that is RA and RB. So first you have to find out the reaction at both ends by taking the external loading. So this is the free bending moment reactions in simply supported condition, figure 1b, this one. This is figure 1b, simply supported condition. Let RA and RB be the support reaction at ends A and B respectively. Then you have to find out what is the reaction at A and what is the reaction at B. So for reaction at B, you have to take moment about A. RB into 4 is equal to 15 into 2 into 1. RB into 4 is equal to 15 into 2 into 1. Then RB is equal to 7.5 kilonewton. Then you have to find out what is the reaction at A. So you have to take the sum of the vertical force is equal to 0. That is the upward force is equal to downward force. So the upward force is equal to RA plus RB and the downward force is equal to 15 into 2. So RA plus RB is equal to 15 into 2, 30. Then you can find out what is the reaction at A. RA is equal to 30 minus 7.5 is equal to 22.5 kilonewton. Then after getting the reaction at A and B, then you can draw the free bending moment diagram. So you have to find out the moment at a distance x from the support A between A and C. So here you have to find out what is the moment at a distance x from the support A. So the moment at a distance x from the support A is equal to RA into x minus 15 into x by 2. RA into x minus 15 into x square by 2. But you know RA is equal to 22.5. So mx is equal to 22.5x minus 15 x square by 2. Then you have to find out what is the free BMT at A, at C and at B. So from this equation you can find out what is the free BMT at A and at C. If you will put x is equal to 0, then you will get the moment at A. If you will put x is equal to 2 meter, then you will get what is the moment at C. So when x is equal to 0, ma is equal to 0. When x is equal to 2 meter, so here you put 2 meter. So mc is equal to 22.5 into 2 minus 15 into 2 square by 2 is equal to 15 kilonewton meter. So this is the moment at the C. And you know that is the moment at B is equal to 0. Here the moment is 0. Then you can draw the bending moment diagram, free bending moment diagram. Up to A to C, this is the diagram is parabolic as the load is UDL, then the diagram is linear from C to B. So this portion is parabolic and this portion is linear. So this is the free bending moment diagram. But you know, when the load is present eccentrically, that is small a distance from the support A and small b distance from the support B, and the length of the beam is L. So this case you know what is the fixed end moment at the end A and at the end B. So the fixed end moment at the end A is equal to minus WAB square by L square. Minus WAB square by L square is equal to MA. Similarly, MB is equal to minus WA square B by L square. This is the formula. So using this formula you can find out. You have to apply this moment in this problem. So here you have to take the elementary concentrated load. Here you are taking the elementary concentrated load. So W dx load is acting on the elemental length dx. So this is you have to take as a concentrated load. So you have to find out what is the moment this side and what is the moment this side. So this side the moment dma is equal to minus W dx into x into 4 minus x square by 4 square. Similarly, dmb is equal to minus W dx into x square into L minus x, that is 4 minus x divided by 4 square. Then after knowing the dma, dmb for this elemental length concentrated load, then after integrating from 0 to 2, because this is the x value, so if x is equal to 0 here, x is equal to 2, that is the position C. So when you will integrate the expression from 0 to 2, then we will find out what is the piston moment at A and B due to this UDL. Due to elementary load W dx, piston moments dma and dmp are dma is equal to minus W dx into x L minus x whole square by L square. dmb is equal to minus W dx x square into L minus x by L square. So this is the moment due to the elementary load W into dx. Then you can find out the total moment ma and mb by integrating from 0 to 2. So ma is equal to minus 0 to 2, 15 dx into x 4 minus x whole square by whole square. Then ma is equal to this one minus 0 to 2, 15 dx x then 16 plus x square minus 8x by 16. Then after integrating, then after putting the limit 0 to 2, so you get the moment, the piston moment at A is equal to minus 13.75 kilonewton meter. So this is the piston moment at the end A. Similarly, you can find out the MB. So MB is equal to minus 0 to 2, 15 dx into x square into 4 minus x by 4 square. So after putting the value, after taking the integration of this expression, then after putting the limit 0 to 2, then you get the piston moment at B is equal to minus 6.25 kilonewton meter. MB is equal to minus 6.25 kilonewton meter. Then after knowing the value of M and MB, then you can draw the combined bending moment diagram. So this is the value MA 13.75 and MB 6.25. So this is the negative bending moment diagram, and this is the free bending moment diagram, positive bending moment diagram, and this is the final bending moment diagram. This is negative, this is positive, and this is negative. And here this is the final bending moment diagram. Here you have to find out the point of contraflexion. This is one point of contraflexion and this is another point of contraflexion. And also you have to find out the maximum positive bending moment here. So where the shear force is 0, so at that position you will get the maximum positive bending moment. So after getting the MA and MB, you can draw the final bending moment diagram or combined bending moment diagram. Then for shear force, so you have to take the load and the moments. After getting the moments and you know the load, by taking the load and moments, you have to find out again the reaction at both ends. So this reaction you have to take R A dash and RB dash. So this reaction you have to find out. You can find out what is the shear force at different positions. Then you can draw the shear force diagram. So here you have to take the external load 15 kilonewton by meter, and also you have to take the moment at both ends. MA you got 13.75, MB you got 6.25. Then by taking this moment and load, you have to find out what is the reaction at both ends, RA dash and RB dash. For reaction at B, by taking moment about A, you have to take the moment about A. So RB dash into 4, this is anti-clockwise positive, and this moment is also anti-clockwise positive. RB dash into 4 plus MA, and this moment is clockwise negative, minus MB, and due to this load, the moment is clockwise. 15 into 2 into 1, minus 15 into 2 into 1 is equal to 0. Then you can find out what is the reaction at B dash. RB dash is equal to 5.625 kilonewton. So here RB dash is equal to 5.625 kilonewton. Then by taking the summation of vertical force is equal to 0, that is upward force is equal to downward force, you can find out what is the reaction at A, that is RA dash. RA dash plus RB dash is equal to the total downward force, 15 into 2. RA dash plus RB dash is equal to 15 into 2 is equal to 30. Then RA dash is equal to 24.375 kilonewton. Then after knowing the RA dash and RB dash, then you can find out what is the shear force at different position. Shear force at B is equal to FB is equal to minus RB dash, right side upward force negative. Then shear force at C remain constant, that is minus RB dash. RB dash is equal to 5.625. So shear force at B is equal to minus 5.625 kilonewton, and shear force at C is equal to also minus 5.625 kilonewton. Then what is the shear force at A? So then this is the UDL, downward UDL. So you have to take plus 15 into 2 minus 5.625 plus 15 into 2. Then you will get what is the shear force at A. So shear force at B is equal to FB minus RB dash minus 5.625 kilonewton. Shear force at C is equal to FC. This is equal to minus RB dash is equal to minus 5.625 kilonewton. Then shear force at A is equal to FA is equal to minus RB dash plus the downward load 15 into 2. This is equal to minus 5.625 plus 30 is equal to 24.375 kilonewton. So this is equal to RA dash. So here you got RA dash is equal to 24.375 kilonewton. Then after getting the shear force value, then you can draw the shear force diagram. So this is the shear force. So here minus 5.625 kilonewton, and at the C also minus 5.625 kilonewton. Then due to UDL, so this the diagram is linear, and here you get, here you take 24.375 kilonewton positive this side, this is negative, and this portion is linear due to uniform distributed load, and here this is constant. This is the shear force diagram. So this is positive and this is negative. So here the shear force changes sign, you get the maximum bending moment at this position. So the maximum bending moment, so you have to find out this distance. Then you can find out what is the bending moment, maximum bending moment. Or you can take the shear force is equal to 0. You have to take a shear force at a distance x from the support A, and you have to make the shear force is equal to 0. Then after knowing the x value, then by putting this x value in the bending moment equation, you get the maximum bending moment. Or you can find out by taking the two similar triangle, this by this is equal to this by this, then you can find out what is this distance. Then after knowing this distance, you can find out what is the maximum bending moment. So the point of contraflexure, also you have to find out the point of contraflexure. This is one point of contraflexure, this is. So you have to take a section at a distance x from the support A, and you have to find out what is the bending moment here, and you have to equate that bending moment to 0. Then you get what is the point of contraflexure distance, this one. Similarly, this side also you have to take one section here at a distance x from the support B. Then you have to find out what is the bending moment at this position. Then you have to make this bending moment is equal to 0. Then you will get this distance, this point of contraflexure distance. Here you have to take one section and you have to find out the bending moment, and here you have to take the section and you have to take the bending moment. Then you have to equate this to bending moment is equal to 0. Then you get what is the point of contraflexure distance. This is moment at a distance x from the support A between A and C is equal to this one. This is the moment mx is equal to 24.375 x. This is 24.375 this reaction into x and this is clockwise positive, and this moment anti-clockwise negative minus 13.75, and due to this UDL also anti-clockwise negative. 15 into x by 2, 24.375x minus 13.75 minus 15 x square by 2. Then you know at the point of contrapressure mx is equal to 0. Then you have to equate this equation to 0. Then you get so this is the value, x is equal to 0.89 meter. Then for another point of contrapressure, taking moment at a distance y from the support B between B and C. Here you have to take the section at a distance y from the support B, and you have to find out the moment my. My is equal to Rb into y minus 6.25. Rb into y minus 6.25 is equal to 0. Then you can find out what is the distance. Y is equal to 1.11 meter. So the first point of contrapressure 0.89 meter, this one, from this to this distance 0.89, and from this to this distance 1.11 meter, this one. This is the 2 point of contrapressure distance. Then you can find out what is the maximum bending moment. So you have to find out this one. So where the shear force is 0, at that position you get the maximum bending moment, positive bending moment, maximum positive bending moment. So for maximum bending moment, the maximum bending moment will be obtained where the shear force is 0. So first you have to find out what is the shear force at a distance x from the support A. Then you have to equate that shear force to 0. So Fx is equal to 24.375 minus 15x. So this is 24.375. You have to take the shear force here. So this is 24.375, and here minus 15 into x. This is UDL, and for the distance x, so the total downward force is equal to 15 into x. So 24.375 minus 15x is equal to 0. Then you can find out the x value. X is equal to 1.625 meter. So at a distance 1.625 meter from the support A, you will get the maximum bending moment. So you know the mx is equal to this one. Already you know mx is equal to 24.375x minus 13.75 minus 15x square by 2. Then by putting this value, x value, you get the maximum moment. Mx is equal to 6.054 kilonewton meter. This is the maximum moment, positive moment. This is the maximum positive moment, 6.054 kilonewton meter. Here also you have to find out what is the moment. So this moment you can find out. So by taking, this is one triangle and this is another triangle. So here you know this distance, because this total is 13.75, this is 6.25. So this portion is equal to 7.5. So this side by this side is equal to this side by this side. That is 7.5 by 4 is equal to P by 2. Then you get the P value. P is equal to 3.75. Then after knowing the P, so you know this portion 6.25, 3.75. So from this total, the total is 15 kilonewton meter, 3 BMD. So from this total, so you deduct this portion, then you get what is the positive moment at C. So positive moment at C is equal to 15 minus 6.25 minus 3.75 is equal to 5 kilonewton meter. So this is the positive moment at C. So this is the final bending moment diagram, and this is the final shear force diagram. Then coming to the second question, find the fixed end moments and plot bending moment diagram and shear force diagram for the beam loaded as shown in figure. So this is the fixed beam. The span is given 8 meter, and here this is the 2 meter, this is 2 meter, and this is 4 meter. The load is present C to D, that is after 2 meter length from the support A, then the UDL is present for a length of 2 meter, that is C and D. AD length 2 meter, then CD length the UDL is present, and BC length is 4 meter, and W is given 16 kilonewton by meter, and the length is given 8 meter. So here also you have to take a small element dx at a distance x from the support A, and here you have to take W into dx. The total elementary load is equal to W into dx, and W is given 16, that is 16 into dx. Load acting on an elemental distance dx is equal to W into dx, 16 into dx. So due to this elemental load, you have to find out the friction moments. So here also you have to take the simply supported condition, and you have to draw the free bending moment diagram. Then you have to find out the fixed bending moment by taking this elemental load, then by integrating from 2 to 4, because here the load is present from after 2 meter, and that is having up to 4 meter. So you have to take the integration limit here 2 to 4, then you can find out what is the friction moment at A and B, M and NB. Then after getting the M and NB, you can draw the combined bending moment diagram. Then for shear force, you have to take total moment and the load. Then you have to find out what is the reaction, once again RA dash RB dash. Then after knowing RA dash and RB dash, you can find out the shear force at different position. Then you can draw the shear force diagram. Here also you can find out the point of contraflexure and the maximum bending moment, as you have calculated in question number 1. So this is the fixed beam with the UDL at the distance C to D 2 meter. Then this is the simply supported condition. Here only you have to take the load, and you have to find out what is the reaction at both ends. Then after getting the reaction, then you can draw the free bending moment diagram. You have to find out the free bending moment at different positions. Then you have to find out the free bending moment diagram. You have to find out what is the moment at A, what is the moment at D, what is the moment at C, and what is the moment at B. Then you have to find out what is the fixed end moment M and FB, and you have to draw the fixed bending moment diagram. Then after combining this free and fixed bending moment diagram, you get the final bending moment diagram. So for free bending moment diagram, first you find out the reaction. In simply supported condition, let RA and RB be the support reaction at end A and B respectively, taking moment about A. RB into 8 is equal to 16 into 2 into 3. So you have to take the moment about A. So you have to find out RB into 8 is equal to 16 into 2, and from this to this centroidal 1 plus 2, 3. 16 into 2 into 3. 16 into 2 into 3. So RB is equal to 12 kilonewton. Then you can find out the RA by taking the summation of vertical force is equal to 0. That is, upward force is equal to downward force. So upward force is equal to RA plus RB, and downward force is equal to 16 into 2, this length, and the load is given 16, 32. Then RA you can find out 32 minus 12 is equal to 20 kilonewton. Then you can find out the free bending moment at A 0. Then you have to find out the bending moment at a distance x from the support A between C and D. So here you have to take the bending moment at a distance x from the support A. Here you have to find out what is the bending moment. That is RA into x minus 16 into x minus 2 into x minus 2 by 2. This is RA 20 into x minus 16 x minus 2 into x minus 2 by 2. This is the moment at a distance x from the support A. Then by putting x is equal to 2 meter, if you put the x is equal to 2 meter, you get what is the moment at D. And if you put x is equal to 4 meter, then you get what is the moment at C. X is equal to 2, you get the moment at D, and x is equal to 4, you get the moment at C. X is equal to 2 meter, MD is equal to 20 into 2, 40 kilonewton meter. X is equal to 4, MC is equal to 20 into 4 minus 16 into 2 into 1, 48 kilonewton meter. Then MB is equal to 0. At the end, the moment is 0. Then you can draw the free bending moment diagram. 0, 0, 40, 48. MD 40, MC 48. and here this portion is parabolic and this is linear and this is linear. This is the free bending moment diagram. Then you have to find out the MA and MB. This is the for fixed bending moment. Fixed end moments M and MB due to concentrated load W at distance A and B from A and B respectively are, you know, this is the formula. MA is equal to minus WAB square by L square, MB is equal to minus WA square B by L square. Then by using this formula, you can find out the moment for the elementary load. Due to elementary load W dx, fixed end moments DMA and DMB are DMA is equal to minus W into dx into x L minus x whole square by L square. Similarly, DMB is equal to minus W into dx into x square into L minus x by L square. This is the moment due to the elementary load. But here you have to find out the moment at the end A, MA and MB by integrating from the limit x is equal to 2 to x is equal to 4 meter. So here you have to take the integration limit 2 to 4. So minus MA is equal to minus 2 to 4 16 dx into x 8 minus x whole square by 8 square. Then after taking the integration, then after putting the limit 2 to 4, so you get the moment at the end A, MA is equal to minus 36.333 kilonewton meter. Similarly, you can find out the moment MB minus 2 to 4 16 dx into x square into 8 minus x by 8 square. Then after taking the integration and putting the limit 2 to 4, then you get the moment at the end B, MB is equal to minus 22.333 kilonewton meter. Then after knowing this moment, you can draw the combined bending moment diagram. So this is 36.333 and here this is 22.333 kilonewton meter. Then this is the negative bending moment diagram. This is fixed BMD and this is the free bending moment diagram. You have to combine these two diagrams, positive and negative. So this portion cancel. So this is negative, this is positive and this is negative. This is the combined bending moment diagram. This point is the point of contraflexure and this point is also point of contraflexure. You have to find out these 2 points and this is the maximum bending moment. This is the maximum bending moment you have to find out, and here you have to find out also what is the positive moment at D and what is the positive moment at C. By taking the similar triangle, you have to take, this is the triangle, this is one triangle, this is another triangle. Then by using this triangle, because you know this ordinate, you know this ordinate, so you can know this one 14 kilonewton meter divided by this total length 8 is equal to Q by 6 is equal to P by 4. This is the, then you can find out what is P and Q. Then after knowing P and Q, you can find out this distance, the positive moment at D and positive moment at C, because you have to deduct, you know, this total ordinate 40 kilonewton meter. So you got here Q and you know this ordinate 22.333. So after deducting Q and 22.333, you can find out what is this ordinate. This is the moment, positive moment at D. Similarly, you can find out what is the positive moment at C. 48 minus 22.333 minus 7, 18.667. And you have to find out the maximum positive moment where the shear force is 0. So first you have to find out the reaction by taking the load and the moment. Then after knowing the reaction, you have to find out the shear force at different position. Then you can plot the shear force diagram. Then after getting the shear force, you have to find out what is the maximum bending moment. Here you have to take the load and the moment. So load is given 16 kilonewton meter and moment you got 36.333 kilonewton meter MA, MB you got 22.333 kilonewton meter. Then by taking this load and the moment, so you have to find out what is the reaction RB dash 10.25 kilonewton. By taking moment about A, you can find out what is the reaction at B, RB dash. Then by taking the upward force is equal to downward force, you can find out what is the reaction at A, RA dash. So RA dash is equal to 32 minus 10.25, 21.75 kilonewton. After knowing RA dash and RB dash, then you can find out what is the shear force at B, shear force at C, shear force at D, and shear force at A. So shear force at B is equal to minus RB dash, right side of pole force, minus 10.25 kilonewton, and this is remain constant up to C. So at C also, shear force at C, FC is equal to minus 10.25, then shear force at D is equal to minus 10.25 plus 16 into 2. Minus 10.25 plus 16 into 2, that is 30 plus 32, minus 10.25 plus 32 is equal to 21.75 kilonewton. Then the shear force at A is equal to constant, 21.75 kilonewton, that is equal to RA dash. This is the shear force. Then after getting the shear force, you can draw the shear force diagram. Shear force at B minus 10.25 and shear force at C minus 10.25, shear force at D plus 21.75 and shear force at A plus 21.75. This one at D 21.75, at A 21.75. This is minus. So here this below this negative, above this x is positive. This is the shear force diagram, and here you get the maximum bending moment because the shear force is 0 here. So you can find out what is the maximum bending moment here. You have to find out this distance, then after putting this distance you can find out, or else you can find out, you have to find out what is the shear force at a distance x from the support A, Fx, then you have to equate Fx is equal to 0, then you can find out the position of the maximum bending moment x, because you have to take Fx is equal to 0, you can find out x. Then after knowing x, you can, after putting the value of x in mx, after putting the value of x in mx, you have to find out what is the bending moment here, also mx, then you can find out what is the maximum bending moment. So this is the final bending moment diagram. This is the point of contraflexure, and here you got, this is the positive bending moment at D, positive bending moment at C, and this is the negative bending moment, fixed moment at A and B, negative, negative, positive, and this is maximum positive moment, and this is the shear force diagram, negative and positive. So this is all about the analysis of fixed beam with UDL for some distance. Now all are clear how to solve the fixed beam with uniform distributed load present for some length.